right, so on a lot of difficult geometry questions, it's important to just think critically about how we could manipulate the shape and not necessarily think about unpacking all of the algebra, okay? So let's take statement 2 on its own, for example, first. Statement 2 says ABC is isosceles, and that means it's a 45, 45, 90 right triangle because it means that two angles are equal to each other. And since we already have a 90-degree angle, I know that that can't be paired with another 90-degree angle, or we wouldn't have any degrees left over for the third angle because the three angles always add up to 180. So I know it's a 45, 45, 90. Now, can I tell if this triangle is the same as the area of this triangle, if the areas match? Well, I don't know anything about how long this top line is, and technically it could go on for a very long time, and that would mean that it could be very large or it could be very short, and that would mean that we would get a very small area. These things are unaffected by the information we were given, so these two situations are both possible, and that means that since there's more than one situation, and I believe that we could find a situation where I could set these two triangles equal by following these rules, these areas may or may not be equal, and that means that statement 2 is insufficient. All right, now statement 1 on its own, if we kind of play a similar thought process, AC squared is equal to 2AD squared. Well, so let's pick kind of like let's pick a value for AD on its own first, and let's make AD squared equal to 1. So it's 1 squared. And I'm just going to draw out another version of this triangle, smaller, but something we can work with. Okay, so if I know that we have right angles here, if I know that AD is 1 and AC would then be, since I would have 2 is equal to AC squared, that would mean AC is equal to root 2, which would make this height root 2. Now, is it possible to get these two triangles to be equivalent to one another in terms of area? Well, again, I don't know anything about this line here. It could be really long, in which case we could extend this over here, and then we could connect these tops, all while keeping this information static and without even rotating these very much at all. So this would obviously rotate up a little bit if I rotated it, because the right angle has to be like that off of this. But we can move these around without changing the value that we stuck in here that kept true to statement 1. So statement 1 leads to multiple situations as well, and I bet we could play with this until we got two situations that were equivalent to each other for area. So this is also going to be insufficient. But when we take the two statements together, what we find is that we have a very particular set of rules. And that is, first, as we focus on this triangle, in the situation I've chosen with root 2, we would know that this is root 2 and this is root 2 in a 45, 45, 90 triangle. And if that's true, we know that the ratio in a 45, 90 right triangle is x to x to x root 2, meaning root 2, and then root 2 times root 2, which is equal to 2. The hypotenuse here would be 2, and I'll draw that on the inside there. Now, if we also have a triangle where the one length here is 1, and we know this length is 2, if I multiply these together, we get an area of 2. If I multiply these two together, 2 over 2, right? Because we have to divide every triangle, base times height divided by 2, base, height divided by 2. So we get an area of 1 for the top triangle. The bottom triangle would be root 2 times root 2 divided by 2, and root 2 times root 2 gives a total of 2 on top, divided by 2 gives an area of 1 as well. And what we find out is when we follow these rules, we get the same area for both triangles. And this is an odd thing, but it has to do with the relationship between the hypotenuse of an isosceles triangle and that ratio to its side. And so this locked it in. We found that the areas were equivalent to each other. It wasn't just by chance. It would actually work with any number. And we could test another situation, but I think I'm very confident that this is answer choice C. Both statements together are sufficient to answer the question that yes, these two triangles are equal in area.